All right. How many moles of HCl are in 25 milliliters of a 0.125 molar solution? You can go about this a couple different ways. First, you have to recognize that a 0.125 molar solution means that there are going to be 0.125 moles in 1 liter of solution. That's what molar means, moles per liter. So there's that many moles in a liter. So if you got an answer of more than 0.125, you know it's going to be way less than 0.125 because this is a fraction of a liter. So if it's 0.125 moles in the whole liter of solution equals how many moles in 25 milliliters or 0.025 liters? So that's one way is to set it up like a proportion. Realize that the concentration has to be the same because it's 25 milliliters sample. So 0.125 in 1 liter has to be the same as some number divided by 0.25. The other way to do it is to set it up in a problem and say 0.125 moles per 1 liter multiplied by 0.025 liters. Liters will cancel and you get moles. I don't know what that comes out to. It's 0.125 times 0.025 is, either way you do it, 0.00312 moles of HCl, or 3.125 times 10 to the minus 3 moles. All right. Questions about that one? All right. What is the molar concentration of a 500 milliliter solution containing 2.5 grams of calcium chloride? Well, again, molar concentration is going to be moles per liter. You're given a 500 milliliter solution and 2.5 grams. So we have to convert the 2.5 grams to moles. Calcium chloride is CaCl2. So you've got 2.5 grams. You right? Okay. All right. And then we're going to want to convert grams to moles. So for calcium chloride, that would be 40. Okay. Yeah, let's just say, all right, we'll say 111. I mean, if it's close, you're going to get a similar thing. So you're going to come out with 0.0225 moles of calcium chloride. But then it's a 500 milliliter solution. So to find the concentration, we've got to put those 0.0225 moles of calcium chloride in 0.5 liters of solution. So that's going to equal 0.0450 molar. So the concentration will be 0.045 molar. Good job. All right. Then finally, looking at osmosis, semi-permeable membrane separates two compartments, A and B. A contains a 2% starch solution. Why is it important that it's a starch solution?
Oh, yeah. Because the starch won't go through. It's
right. Because the starch won't go through the semi-permeable membrane. So we're only looking at water, the transfer of water. If it were there other ions.
So, okay, no. I'm just basing it off of the starch going through. I didn't think of the water. I mean, obviously right. The water's going to go. Starch
doesn't go through semi-permeable membrane. Water will go through, and that'll be the osmosis. So If the levels in A and B are equal initially, circle the diagram that illustrates the final levels. So here we have, let's say this is our initial. So it may, well, it's not going to say the same, but let's say this is our initial. So A contains a 2% solution and B contains a 0.5%. So which direction does the water move? Well, the water is going to move to try to equalize the concentrations. So it's going to move from where there's more water per solute to where there's less water per solute, which is this direction. So we're going to end up with number 3. And so your explanation should be something about that it's going to go from, it's going to try to equalize the concentrations and go from the area of lower solute concentration to the area of higher solute concentration through the osmosis. Now look at 3. So the other question that I could ask about something like this, and that I would probably at some point, is to ask, rather than asking about what's going to happen, ask about the osmotic pressure. So which direction is the osmotic pressure? Draw. It's the way that, because the solvent is moving that way, so that's the pressure pushing up, pushing that direction. So there's going to be a positive osmotic pressure on the right side and a lower osmotic pressure on the left side.
I was just thinking of the start, and I'm like, well, both of them are going to stay. If the start equal, they're going to stay, you know. But I forgot that the water also.
The water moves, right? That's how osmosis works. All right, and then the last question. We have a solubility chart, just like in the last lab. And we're going to look at glucose right here, which is this reddish, orangish line here. So we want to look at what temperature would 65 grams of glucose dissolve in 50 milliliters of water. So we have solubility here is grams solute per 100 grams of water. And we're trying to find out about 65 grams in 50 milliliters of water. So 65 grams glucose per 50 grams of water is how much glucose in 100 grams of water. Should be double, right? So that's 130 grams. So the same proportion there, that same solubility, would be 130 grams of glucose per 100 grams of water. So we got to look at where 130 grams is. That would be right here. So above 40 degrees C, 130 grams of glucose would dissolve in 100 grams of water. Same, yeah. I think they're all worth 2 points. Oh yeah, I guess that one would be worth 4 points. This is some weird calculations. 2, 2, 2. Oh no, it should be 2. These should also be 2. So these should also be 2. That's the typo, so that they're all 2. Yeah. Well, I meant to make them all even. Sorry. All right, so we'll have another quiz next week on acids and bases. Try again. That one you can do? Okay, good. Good. So next Tuesday, acids and bases. Good. Hope that happens. Acids and bases. Probably not. Maybe.
It was fun.
It's helpful because you see the mistakes your partner is making versus the mistakes that you're making, so that you learn more.
That's good.
So you should do it next time. You can write an essay on why this is better.
No, we were actually working very well under the online quiz. We have a quiz this week.
All right, so before we go on to the next chapter, start talking about nuclear chemistry, I want to go back to acids and bases for a little bit and talk about what's going to come up in lab today. At lab today, most of it is pretty straightforward. You're just testing pHs of stuff. That's like a big part of the lab. Using a bunch of different methods to test pH. But the last part of the lab is an important acid-base technique. It's actually important for lots of different techniques, but it's called titration. And it's worth spending a minute to talk about what that is and why it's important. Oh yeah, sorry. I always forget there's a dark spot up there. Titration is not just used with acids and bases. It's sort of this classic lab experiment that if you've ever taken any chemistry before, you probably did a titration. If you take chemistry again, you will. But it's really actually still used a lot in analysis. So when you send samples to a lab, medical samples, if they're testing for certain types of dissolved ions or other things, they'll use titration. Standard solutions, when you buy or use standardized solutions of different kinds of solutes, those will have to be titrated to figure out what that is. I mean, even here in our department, when we go upstairs, you'll see there, we always have bottles of whatever concentration, something or other. Those concentrations are all confirmed through titration. So it's a really important process in a lot of different areas. And it basically involves adding an amount of something you know to amount of something you don't know to figure out the one that you don't know. So let's see what this looks like kind of in practice. The titration that we're going to do today, we'll just look at that one for an example, is going to be the neutralization reaction. So what's a neutralization reaction? You remember? That can be, yeah, but more generally, it's any time an acid and a base react with each other. That's called neutralization. And so it always forms water, and then some kind of a salt made from the other parts. So it looks kind of like a double replacement reaction. So this is acetic acid, sodium hydroxide, water, and then we would call this sodium acetate. All right, so you put an acid and a base together, you make water. That's the basis of a neutralization reaction. Is this reaction balanced? Can you tell just kind of by looking without counting everything out? I think if you think about it in terms of ions, you probably can. So you see that the C2H3O2 is here, and then also here. H and OH combined to make the H2O, and then the sodium. So this is just balanced as is. That means that acetic acid and sodium hydroxide are always going to neutralize each other in a 1-to-1 ratio. So if you do this reaction to completion, meaning you neutralize all of it together, and there's nothing left over, you should react an equimolar amount, so the same number of moles of one with the same number of moles of the other. In other words, if I have, let's say, 0.23 moles of this, I would need exactly 0.23 moles of this to react with it fully neutralize it. All right. So the way we experience neutralization in lab, which you'll see in an hour or so, a couple hours, is that we will measure a pH, or we'll actually use an indicator, which is a color change of pH. When there is just acid, it's going to be a low pH, right? It's going to be acidic. And then as we add base, it will get less and less acidic until it gets to that neutralization point where it becomes totally neutral. So when 0.23 moles of one react with 0.23 moles of the other, it becomes neutral. There's no longer any acid or base around, it's just water. You see how that would work? So the way that works experimentally is like this. We take a flask, and we put some of the acetic acid in it. And then into that flask, we use a burette and we dispense some sodium hydroxide. Do you remember burettes at all? There's a little like stopcock on the side. And these are the ones, we talked about these near the beginning of class because they're a little unusual in that they seem to count backwards. Instead of 0 being at the bottom, 0 is at the top. The reason for that is because we don't want to know how much stuff is in the burette. We want to know how much stuff is coming out of it, how much has come out. So we put this, a sodium hydroxide solution in the burette, and we dispense that solution until we reach the neutralization point, until there's no more acid, no more base. It's all neutralized in the middle. So we're going to dispense this out of here, and this level is going to go from, let's say, here down to here. How do we know when it hits the neutralization point? It turns color. We use what's called an indicator. Oh, you don't need to write this down. We use what's called an indicator, which is just a chemical that turns color in one side or the other of the acid-base spectrum. So in this case, we're using something called phenolphthalein. You just put in a couple drops. And when phenolphthalein is in an acidic environment, it's clear, has no color. When it is in a basic environment, it's pink. So when that solution just first turns a little bit of pink, then we know we're no longer in an acidic environment. We've switched over.
So how do you know it's not?
Because you want, well, that's the trick, is you want to do the titration just at the point where it turns pink, not where it goes too far, because now it's becoming more basic instead. And so I'll show you a picture of that, what that looks like in a minute. All right, so then how this tells us what, or the point of doing all this is not just mixing these things together so we make a nice color. The point of doing this is we have an unknown acetic acid concentration. We don't know the concentration of it. But we have a known sodium hydroxide concentration, and in this case it's going to be 0.1099 molar NaOH. Now, just like the question on the quiz, if you know exactly how much volume of a known concentration you have, you can calculate the amount of moles in that amount. So let's say that this titration, you do this, and it first turns pink when you reach, I don't know what the actual number is, but let's say it's 13.10 milliliters . Makes it turn pink. So you've added 13.10 milliliters of the sodium hydroxide solution, drop by drop at the end, and you finally get that perfect pink color. That means that if we've got 0.1099 moles per liter, and we put in 0.0131 liters, which is 13 milliliters, 13.1 milliliters. Calculate that out a second. 0.1099. That means we've added exactly 0.00144 moles of sodium hydroxide. So there it comes from. So we have a known concentration, and we know how much of it we used. So we know exactly how many moles of sodium hydroxide we added to neutralize the solution. So if we go back to our equation then, if instead of 0.23 moles, so if we know then that we added that it took exactly 0.00144 moles of sodium hydroxide to neutralize the acid, how many moles of acid must have been there in the first place? The same. Since they react in a 1-to-1 ratio, we know that there must have been the same number of moles of acetic acid as we added of sodium hydroxide to make them all balance out. And then assuming we know how much acetic acid is here, we now know how many moles, and we know the volume, and so we can calculate the concentration of the unknown acetic acid. In this experiment, I think you're supposed to add exactly 2 milliliters of acetic acid. So if we know that there are 0.0144 moles, and we know that it's in 2 milliliters, then we can divide those and figure out what the molar concentration of the acetic acid is. So that's what's going to be happening in lab today. Now, a couple other things about this. First of all, let's look at Blackboard for a second, because this is where I have the picture. Yeah, so if you saw those pictures down at the bottom when you were printing out the labs today. I'm going to turn off the lights so you can see this a little bit better. Now, if it looks like that, you've gone too far. And like you're talking about, that's become basic now. Because we don't want to know when it's really basic. We want to know when it just turns. And it's literally one drop that's going to make the difference between clear and pink. And then one more drop is going to be way too pink. So what you want is this. The pink in the solution is so light that you can't even really tell that it's pink unless you compare with a clear solution next to it. If you just looked at that by yourself, you might not even see that it was pink until you compare it with another clear solution. So there's just the faintest hint of pink. That's what you're shooting for. Now, a drop size is a drop size. So sometimes just the fact that a drop is as big as it is means you're not going to get to that it's going to go a little bit over. But if you get this sort of deep pink, you know you've got too far, and you got to do it again. All right, so to do this without it taking hours, because we don't, by that point we won't really have hours, there are a couple tricks to make it go well.
Thank you.
And you'll see this in your lab manual. But the first thing you're going to do is called a rough titration. And everybody always does it this way first. Basically, you're just not being very careful. You dump a bunch in, you dump a bunch more in, you dump a bunch more in, you keep dumping it in until you get to that pink color. And you're almost certainly going to overshoot it. But the point is to figure out about how long it's going to take till you overshoot it. So let's say you're dumping it in, you're dumping it in, you're dumping it in, and you realize that like 14 milliliters in, or 15 milliliters in, or whatever it is, it got really pink, really dark pink. So you write that down. Okay, took about 15 milliliters, got really dark pink. Now you know for the next time that you're going to have to stop it way earlier than that. So what that tells you for the next time is you can go as fast as you want. You can just open the thing up and let it flow until you get to, say, 13 and a half milliliters, something close to that, and then you can start being really careful. And you can actually set the stopcock to where it's dripping at whatever rate you want. So you can make it go drip, 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 or when you're getting closer, you can make it go drip, drip, drip. And then while it's doing that, you're kind of swirling the thing around. And then as soon as you see that color change, you can just stop it, and you're done. You're good. All right? So you'll get used to it and practice with the stopcock a little bit, because if you kind of let it go too long and overshoot it, it gets too pink, got to do it again. So then after that first rough titration, you're going to do at least 2 more. Because you want at least 2 good ones to be able to get some decent averages for the numbers to work out. At least 2 good ones. So if you get 2 good ones, great. If not, then you'll do some more. But after you do that first one, after you kind of get used to it, they should go pretty fast. So are there questions about this procedure? Does it make sense? People always have trouble kind of figuring out what's happening in this lab. If you have questions about it, now's the time to ask.
Up in the beginning, when
Yeah.
you came up with that number of the, how did you come up with that 0.00144 moles, aside from Downs? And
Here.
the calculation? So you just know that that's 1-to-1?
Right.
That's all you have to know?
That's all you have to
You
know.
actually have a number, you just know that it's 1-to-1?
Right.
So if you have one number, that's the other.
And that's how titrations work. So you know one number, and then you use it in the equation to find the other one.
They're not always gonna be 1-to-1, right? I mean, are they?
That's true, but you'll always know what they are based on the equation. So if you're using, some acids might be 2-to-1 or 3-to-1 or whatever, but if you have the balanced equation, you can always find the moles of one from the moles of the other. In our case, they'll just be 1-to-1. And in fact, that's why you can use titrations for any kind of reaction. You can try to react until just the right point, and then use moles to moles in the equation to figure out some unknown thing. But we'll use them today in this acid-base way, and we'll look for that nice light pink color. All right. Other questions about that? Okay. Other things about, I guess, I'm not going to start a new topic now because we're almost done anyway, but I'll just talk about the rest of the things involved in the lab today. So you'll be breaking up into groups to do the household products. You'll notice on your sheet there's group 1 and a group 2. So I'll just come around the lab and kind of alternate group 1, group 2, group 1, group 2. What that means is you're only going to test half of them, and then you'll get the information for the other half from another group. And you're going to be testing with litmus paper, with pH paper, with pH meter, and with a universal indicator for several of these different things. The household products, I think you're only testing with the pH meter. A pH meter is an instrument that can actually measure the hydrogen ion concentration and report it as pH. So you'll see it's like a little probe thing, you dip it in there. pH meters like to sit around happily in a buffer solution. So when you're not using it, it should always stay in the buffer solution. And then before you put it in something, you can just spray it off with some water from your water bottle. The other thing that we should note, if anything spills today, note the pH of it. If something spills that is a pH between, let's say, 6 and 8 or thereabouts, that's neutral, and you can probably just clean it up with a paper towel and not worry about it. If something spills with a pH of 1 or a pH of 12 or 14, that could potentially be something caustic that you don't want to get on your hands. So let me know about that, and we should neutralize that spill before we clean it up. So don't just go at it with a paper towel if it's something that's a low pH, something that's very acidic or basic. And then the last thing, I think, I got everything. Well, we'll see. I'm sure I'll find something else also. The pH paper and litmus paper. Have you ever used these before? Have we used them in this class?
I think so.
We use a little litmus paper with the one lab that a lot of people did wrong. Because you're supposed to leave it on top to let the gas turn the paper color, but everybody just dipped it in, so they got a false positive. Yeah. That's good. Yeah.
What did you say about that one group is going to do one thing? I'm sorry, I missed that.
If you look at your sheet for today, the yeah, that one.
Okay.
There are a list of household chemicals somewhere that you're going to measure for the next page here. So you're only going to do half of these or these. Not all.
And how are you going to know which half we're going to do?
I'll come around and just say
Oh,
1, 2, 1, 2, 1,
sorry,
2,
thank you.
and count it up. So anyway, pH paper, litmus paper. pH paper will turn color depending on pH, and then you can compare it with a little scale and see what the pH is. Litmus paper just turns one color. It either turns from blue to red or red to blue, depending on which one it is. The litmus paper is in your drawers, so not in the regular chemical stuff with the other stuff. When you're testing with litmus paper or pH paper and you're testing a sample, you don't dip the paper in the sample. Right? A lot of people do, but that's not the right way to do it. A couple of reasons for that. One, you can contaminate your sample with whatever's on the pH paper. And then secondly, if your sample is not entirely homogeneous, if you just touch it to the top, you're really only measuring the very top of the sample. So what you want to do instead is take a glass stir rod, stir up the sample a little bit, and then take it out and dip and just touch the wet stir rod to the pH paper or the litmus paper. And that will turn it the color, and then you don't have to put the litmus paper. Then to clean off the stir rod, I would just keep a beaker of water at your station so you can just dip it in, swirl it around, and then go on to the next one. All right, makes sense? Okay, so for the titration again, there are multiple things you need to do. It's all, I mean, all the directions are in there, but I wanted to talk about it here. And then lastly, we should discuss one more time about reading a burette. I know we did this a long time ago, but as long as we're going to be using burettes, so burette looks like this. And let's say this is a 2 and this is a 3. So it counts from 0 at the top down to 25 at the bottom. And let's say your solution is something like this. But what is that reading? Two point three. Did I get something different? 25. Okay, any others? Everybody agrees with one of these two?
It goes from 2 to 3.
Yeah.
How could it be more than 1?
It's upside down. The number of zeros at the top to the bottom of the regular.
All right, we'll stop the suspense. These are both wrong. These are both wrong for different reasons.
Oh,
Awesome.
So firstly, when you make a measurement, you always take your measurement based just on the scale that you're looking at. You don't overthink it or try to do more math about it. So you're right that this would actually contain closer to 23 some milliliters. But that's actually making the wrong subtraction or something like that in here. Like for instance, 25 minus 2.3 is not 23.8, right? So what you do is you read right where you see it, which I'm going to say is like here, the bottom of the curve of the liquid. So this is going to be between 2 and 3, so it's 2 point something. It's between the second and the third tick, so that's 2.2 something, and then the last digit needs to be estimated. So let's call that maybe, I don't know, 7. So that should be read as 2.27. Not rounded, right? Have to have the correct number of significant figures. If it were exactly on the line on 2 or 3, it would be 2.00 or 3.00. This is a very precise technique, so we have to make sure to take our measurements accordingly. The nice thing about burettes is it doesn't actually matter, like when we're doing a titration, it doesn't matter where that liquid level starts. So you'll notice in your report sheet, the part where you write down your data, it doesn't say, or it has a spot there for the starting spot and the ending spot. So you don't need to fill up your burette and meticulously make sure that it starts at 0.00 right at the top. Let's say you fill it up and it ends here. So you look at the burette, you read it, 2.27, that's your starting value. All right, and let's say you do your titration. And you end up once it turns pink, it is here. So where would you read that one? Let's say like there. Yeah, 22.62. So we started at 22.27, we ended at 22.62. We subtract those two. All right. Yeah. We subtract those two, and that is the total amount that was added. All right. So you'd have a starting spot, you have an ending spot, you subtract those, and that's how much you've added. That's how the burette works with its readings. So it's not measuring an actual volume that it contains, it's measuring how much is dispensed by where it started and where it ended. Now, if that makes you scared, you don't like that, you'd rather just start at 0 and then measure from 0 so you can just have the number, that's fine. You can just start at 0. There's nothing wrong with that. But this way, you don't have to worry about carefully getting it to 0 first. You just start it and go. So it saves you a little bit of time. Then when you dispense your acetic acid, you'll also be dispensing it from a burette. There's already one set up for everybody to use. You only need 2 milliliters of acetic acid. So you note wherever the liquid starts at, and then you let it go down 2 milliliters, and then you take your flask away and you're all set. You can go. Do it. All right. Ready to do this one? Okay, let's go do it.